With the advent of the James Webb Space Telescope, JWST, the most sophisticated telescope ever constructed, we now have the means to investigate the possibility of extraterrestrial life. As we direct our attention to the nearest star system, Proxima Centauri, which is only 4 light-years away, scientists have made an astounding discovery. Among the planets orbiting this distant star, Proxima B exhibits strange anomalies and artificial lights that defy explanation. These amazing illuminations have baffled the scientific community experts and sparked speculation about the possible presence of intelligent life. Join us as we explore the groundbreaking revelations made by JWST observation of city lights that contradict our understanding of the universe. American astronomers Jill Tarter and Thomas Pearson initiated the Search for Extraterrestrial Intelligence (SETI) project in 1984. This nonprofit endeavor aims to detect spaceborne radio signals, leveraging the unique capabilities of the Allen Telescope Array nestled in the Californian Cascade Mountains. Despite 3 decades of diligent observation, no definitive evidence of extraterrestrial communication has emerged. After that, the success of the JWST launch aided in the quest to examine a range of distances and undiscovered planets orbiting far-off stars. The largest telescope in the world, which is floating roughly 1 million miles from Earth and outfitted with incredibly sensitive detectors, will be used. 20 years ago, there were no known planets outside those in our solar system, but since then, more than 4,000 exoplanets have been discovered orbiting other stars. According to NASA, the universe may contain trillions of exoplanets. The earliest signs of life beyond our solar system may be found in extraterrestrial plant life. While traveling to Jupiter, the Galileo spacecraft turned its instruments back toward Earth and discovered a clear sign of plant life. When sunlight crosses a planet's star, JWST may be able to detect it as it enters the planet's atmosphere. The instrument detected the vegetation red edge, which is a mixture of red and infrared lights reflected by plants. For example, a planet like Earth covered in a jungle should have a strong and easy-to-detect red edge. JWST will measure the red edge of far-off Earth-like planets in the habitable zone around stars, which could be significant signs of life in the exoplanet's atmosphere. Spectroscopy would next be used to identify the light's missing wavelengths. Atoms and molecules in the atmosphere absorb particular wavelengths, resulting in a distinctive fingerprint that JWST can identify. This technique can be used to ascertain the atmosphere's composition and the possibility of life. It is conceivable that life could exist on planets the size of Earth that have atmospheres comparable to our own, with a predominance of oxygen, nitrogen, and carbon dioxide. One might be able to identify technological life by searching for components that aren't often present, such as fluorocarbon chloride. Even earthly life, such as extremophile species, can appear alien at times. These species are a group of bacteria that can survive in environments where other living things would perish. CFCs, chlorofluorocarbons, generated for use in refrigeration and cleaning products would probably be noticeable to aliens monitoring Earth's atmosphere from a distance. If JWST found CFCs in planetary atmospheres, that would be a clear indication of civilization. Some people can survive in strong acids with pH values below 3, while others can tolerate temperatures as low as 4 degrees Fahrenheit. Some people can even withstand heat up to 250 degrees Fahrenheit, while some can be found on Earth in locations where we would not expect to find any life at all. It could be a smart idea to start with those first because planets like Earth are more likely to host life than planets with extreme temperatures or acidic conditions. Ideal contenders might orbit a stable star at temperatures that permit liquid water to exist on their surfaces. Our Sun is classified as a yellow G-type star, which is less frequent and usually has a shorter lifespan in our universe. Red dwarf stars are more common than other stars and have lower temperatures and luminosities than the Sun. Because of their longer lifespans, roughly 40 billion years, there is more time for the formation of life and evolution to produce complex life forms on these planets, increasing the likelihood of studying planets orbiting around these stars. The initial mission of JWST will focus on a single planetary system that has 7 rocky planets the size of Earth orbiting a quiet red dwarf star. It is possible that the surfaces of 3 of the rocky planets in the so-called habitable zone contain liquid water. Because of its planet's confined orbits, a single star emits light identical to our Sun's, although having a considerably smaller and cooler mass. Proxima Centauri, a red dwarf star 4.25 light-years from the Sun, is the best place for humans to see city lights outside of the solar system. Proxima Centauri is our nearest star, and is approximately 600 times fainter than the Sun, meaning that a planet must be 20 times closer to it than Earth is to the Sun in order for it to support life based on liquid water. A planet with 3 times the mass was found by researchers in August 2016 in this habitable zone, which resembles a Goldilocks zone with light intensity just right to melt water. Given that Proxima B orbits its red dwarf star, Proxima Centauri, at a distance of only 4.6 million miles, it is possible that the planet is an airless, lifeless body. Proxima B is exposed to strong solar winds that have the power to completely destroy its atmosphere, but it also receives enough sunlight to maintain temperatures and liquid water that are comparable to those on Earth. Because of its close proximity to Proxima, it is believed to be tidally locked, always appearing on the same side of the star as the Moon does with respect to Earth. Proxima Centauri, which is roughly 18% of the mass of the Sun, burns far less brightly than one might expect for a planet that is only 5% of the distance between Earth and the Sun, which is likely to be a red-hot planet, since only 65% of Earth's energy comes from the Sun. Liquid water could easily exist on Proxima B as long as the planet has an atmosphere to heat it. However, Proxima B is not particularly friendly to life. It is most likely tidally locked, meaning that it always faces the same direction toward the star and creates permanent day and night sides with significant temperature changes. Because of its proximity to Proxima Centauri, the planet also receives 100 times as much high-energy radiation as Earth, including X-rays and ultraviolet light. Proxima B is also bombarded with high-energy particles during star flare-ups. Unless it has a building magnetic field similar to Earth's, Proxima B is not very hospitable. However, there are certain realistic conditions that could make it a pleasant world. Sadly, models suggest that the atmosphere of tidally locked planets may be susceptible to a rapid collapse due to the freezing out of volatile gases on the night side. A planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Because we don't know anything about Proxima's volcanic activity or magnetic field strength, we can't even guess whether or not the planet has an atmosphere. But since an atmosphere presupposes the existence of oceans, and the two taken together presuppose the existence of life, we are desperate to know if Proxima B has a sophisticated civilization. It might have solar panels covering the day side to generate electricity to light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has triggered a race to determine if it transits its star's face as seen from Earth. These transits would let scientists determine the planet's size and mass, which would then enable them to determine its density. Knowing that would validate the planet's rocky makeup and provide information on the materials used to create those rocks during a transit. By traveling through the planet's atmosphere, starlight may reveal information about it, but only 15% of the time would the orbit be in the proper alignment for scientists to see a transit, and the tendency of stars to flare further complicates matters. The star is tricky, according to Columbia University astronomer David Tipping, because its heat causes rocky planets like Proxima B to absorb sunlight and radiate infrared light. but rocky planets also produce a different kind of infrared radiation from stars. Additionally, JWST was built specifically to study infrared light, which is key to determining Proxima B's atmosphere through its infrared heat signature. Moreover, because water is strongly attracted to this part of the spectrum, JWST will be able to see city lights on Proxima B's night side even if they are as dim as those that our civilization uses on Earth's night side. Due to the distinctive spectral edge's capacity to reflect as Proxima rotates around its star, we could detect artificial illumination as long as it was limited to a frequency band that is 1,000 times narrower than the star's. Proxima B's day side is heavily coated with solar panels. Day and night are identical, with cool evening lows following daytime highs. The temperature difference between the day and night sides of Proxima B will depend on whether or not the planet is made entirely of bare rock, because both the ocean and atmosphere conduct heat. In other words, if Proxima B lacks an atmosphere, the day and night sides will differ more in temperature. In fact, because the day side of Proxima Centauri radiates all of the energy it receives from the planet as a black body, we can determine the exact amount of black body radiation that should be present on the night side. On the other hand, the night side will appear as a frozen version of hell. In the event that Proxima B has an atmosphere, it will only take JWST 10 to 20 Earth days to measure the radiation from its two faces after it has successfully completed its orbit around the star. If the temperature between the day and night sides is minimal, we will know that Proxima B has a thick atmosphere that is moving heat around the planet. However, it should take Proxima B less than a day to revolve around its star, compared to 24 hours for Earth to complete one rotation.